please. Thank you. My name is Ikeda with Kyushu University. This is the title of my presentation. In this session, we're going to discuss the research data. And it says platforms, and the next section is on the platform for research in the next session. So the title suggests my presentation is rather closer to the next session. But I'll come back to this point. But I myself use research data and do research. I do that, but also I research the platform. So that's why I am making a presentation on this. Now, in a nutshell, what I'm going to tell you is what is e-science. That's what I've considered. And the organizer gave us a planning document. And the tentative title of my talk was like this: Science and Research Data. Two means there was a previous one, so that's why mine is going to be second. And so this is a case of the upper atmosphere. Now, just the other day, from August to September, there was IEEE academic meeting. There was an international conference on e-science that was held in Munich, Germany, and this was the presentation I made, forecasting aurora substorms, and we using the machine learning from data. And I'll come back to this point later on for details, but I thought that this was expected. However, maybe I shouldn't have thought this, but is this science? That is the question that I asked myself. I thought this was not science. And so my thinking started, and I struggled creating the presentation materials, but I thought, and so we have this seminar, and there's some sort of swell or movement which I feel is going on about data. And, title is Inductive Thinking. Now, I thought some case studies, and I thought that this doesn't really have to do with the current swells. That's what I thought. And I think, broadly speaking, there are two approaches or directions. One, I will give you a more detailed explanation about the pillar of science. The third and fourth pillars both have a big impacts, but when it comes to the impact on research, that may be a little different. And also the previous example, data and software, or data mining or machine learning, using these, if you just do analysis, is that science? Is that enough to make something science? That's the second question. So let's go into substance. Just a little bit, I would like to make a self-introduction. I won't go into details, but when I was with a bachelor, I was with a Department of Physics. I learned physics, and then I shifted to information, and I have been working in the field of information since then. And my career path may be a little different from other people. At the beginning, I was working at a computer center. And so this is a computer center, and high-performance computing, and network and security. These were what I was related with. Now, research may be a little different, so I skip this. But after that, I joined the Kyushu University Library, where I worked. And there, scholarly communication for the infrastructure, like an institutional repository, and automatic identification, RFID, barcode, are the subjects that I researched. And after that, I moved to the Department of Informatics, and I researched bioinformatics, e-science, information retrieval, and database. So when it comes to high-performance computing, which is rather close to e-science, related with e-science, and we have a lot of librarians, and this is close to library, and this is also related to information. And so I think I'm the right person, the most right person in Japan, perhaps, to talk about this subject. So that's why I wanted to make this self-introduction. Now, I deal with data, I research data. And of course, this is not the exhaustive list, but I use two approaches. First is data analysis, or data mining, or machine learning. This is basically this inductive approach. So from data, you try to identify common patterns or knowledge. However, the simulation is something that I also delve into. And the other approach is data research. Information retrieval, repository are the subjects of my study. So, I talked a little bit about the pillars for science, pillars that support science. Now, when we talk about the fourth paradigm, this is often mentioned, so I think many people are familiar with this. Traditional pillars of science, there are two, theory and experimentation. And when it comes to theory, models are hypothesized. In the case of the physics, these kinds of formula are, which allow you to forecast future. This is a deductive approach. In other words, you hypothesize general theory, and in this case, this is movement, and you give initial conditions, and then after several seconds, where it will be can be predicted. On the other hand, on one hand, we have a theory, and this is a Newtonian formula, and in ancient Greece, this has been done. For example, the universe consists of atoms, and at that time, there was no one who tried to prove something. From around the time of Galileo, experimentation started to corroborate things. And so this is the other major pillar that supports science. And from individual phenomenon, the general hypothesis or model are to be generated. And this was the distance of the body, and Hubble said the universe expanding, and this is a graph that shows that. You have results of observation, and you drew a linear line, and that's inductive. And so these are the two traditional pillars. And we have new pillars now. One of them has been used for the last several years, that is simulation, computer simulation. Broadly speaking, this is a deductive approach. You hypothesize a model, and over time, usually over time you try to reproduce the phenomena, and that is compared with the actual data. And in field where the experiment is very difficult to do, for example, the atomic bomb, the forest fire, or earthquakes, or economic activities, this is very useful to reproduce them. So this was quite impactful, and this has been one of the pillars that support science for the last several decades. And the recent one is this inductive approach. There are lots of ways to express this, data-intensive science, data-centric science, and there are some other words that have been coined to express thinking from data. And behind this, you have a network which is now much faster, and also we have sensing technologies that have been developed, and also the data analysis software and tools that have been developed further, and these are in the background of the development of data science. As was suggested in the title, I gave some consideration to some points. Is my example science? And I also considered other examples. Well, I'm not familiar with all the fields, and so well, I don't do simulation much, so these may be, well, they are all computer simulation, but simulation of typhoons, which was mentioned earlier, and also atomic bombs, forest fires. These may be good examples. As I said before, the phenomena that is very difficult to do experiment of can be reproduced. So this had a big impact on science. But when it comes to the impact on the research style, these kinds of researches were rather not open, but these may not have changed much in a closed setting. Computer resource, well, in a distance, for example, you use a supercomputer in the United States. You may do that, but when it comes to research style, is not all that different from traditional research style. Do you use computer right here or next door, or a computer in the cloud? The research style itself may not have changed much. So this is my impression about this third pillar. On the other hand, this is a bit difficult. Fourth pillar. I cited some. Can these be called science? It's a delicate topic, but from data, this has been developing. There has been a lot of advancement in these fields. For example, computer shogi, Japanese chess. These beat the really grand masters. But is this science? Well, I'm not sure. Of course, in the background, there is a result of machine learning and also automatic driving. This is based on pattern recognition or the image recognition. But again, this can work just like human beings. But is this science? I put a question mark here. And flu. From the research records, you forecast a flu. Well, Google does it. But what about this? What is common amongst these case studies? Very high precision recognition or forecast is possible, but on the other hand, you don't go into scientific mechanism. For example, in the case of shogi, Japanese chess, what kind of thinking is happening? You just disregard it. You just learn the patterns, and the machines just put a pawn on the board. So that's why I thought this was not science. And now let's think about the impact of open platforms to research. Now let me begin with my example. I showed you a little bit of this aurora substorms. Aurora explosion, that's what the Japanese word says. I'm not an expert of this, but the aurora brightens and expands, I think. So detailed physical model has not been elucidated yet, but this is within 5 minutes. This is the whole sky pictures, but it happens over a few hours, according to my information. So you have this phenomena, and the mechanism is not known yet. What I did is using machine learning and the solar wind and the geomagnetic field data are used to see when this phenomena happened. Manually, I identified that, and in other words, when it happened and when it didn't happen, there are two patterns, and well, this is the data of when it happened, and well, you give data about not happening. This is called training data about whether such a phenomenon occurred or not, and these are linked, and I put a parameter and gave it to algorithm. Then algorithm come up with a model automatically, and this model, rather than physical model, but this is a learning model, and unknown data, when that is given, then this kind of phenomena will occur. That kind of answer will be given to me. This is a poster presentation. About 80%, 79% precision was observed for the correct precision forecast. So let's take a look at this process of research. What did it do? First, domain expert, Dr. Tanaka. I heard stories from him about data and the characteristics of data. And then you try to locate data. And the one that I used this time is the National Institute of Polar Research, the all-sky image, and this is NASA, solar wind data from NASA, and right after this, there's going to be a presentation by Professor Nose, World Data Center, this geomagnetic field of data of World Data Center were used. As I said before, we created the training data. So students looked at a lot of pictures of aurora and do identification. And so when you come to this stage, then the rest can be done by the machine. So you just give data to the machine learning algorithms. And here libSVM, the very famous machine learning library, was used. And after this, when you have a result and you try to see what the meaning is, and with the domain experts, you have a talk and get that evaluated. And so as you see it here, the data and this one also, software, in a way they can be called open platform. And because of these results, we got this result. And this is open collaboration. I think this can be called open collaboration. You don't know the person who got the data or opened the data, and I don't have a personal connection with the person who created libSVN. But on the shoulders of these people, new results were obtained. And so focus of this workshop is data, but I think software in recent years, the scientific software is evolving. A little while ago in the field of business, LAMP, Linux, Apache, MySQL, and programming language P was there, and the startups were able to create systems cheaply. This was very impactful. To use this well, you need a programming skill. But on the other hand, recently, including R, the programming languages, and scientific libraries focused on science. For example, linear algebra, Fourier transformation, the machine learning, data mining, statistics, and many others. These have become much, much better. And just a while ago, was unthinkable, but quite latest results of machine learning was implemented, and relatively speaking, this can be used very easily. That's a big impact. So the latest data analysis tool is available very easily these days. So with this, what will happen? This may not be a right English, but a finely grained unit of scholarly communication would be made possible. For example, data journals. The Ecological Society of Japan publishes this English journal called the Ecological Journal, and there's a data paper which is one type and recent one, and this one, this is the IPSJ Bioinformatics Journal. The original, in addition to original paper and survey paper, there's also database and software paper. So system or software, if you can generate that, then you can write a journal. Now, to write a paper, you just develop this. So unless you publish a paper, you cannot say you have gotten the results. But this in itself allows you to say you have gotten the results. So with this, using data or using database or software, you can perhaps collaborate with people in other fields. People will collaborate with strangers in other fields, going beyond the time boundaries. Another point, I'll come to the end of my presentation shortly, but I think the fourth paradigm may be effective on complex phenomena. Simpler phenomena are being elucidated, but when it comes to complex phenomena, for example, environmental issues are still remaining. When it comes to these issues, in these fields, the fourth paradigm, the data science, may be promising. In other words, you cannot go closer to mechanism, but with the results, along with the experts, you can think about the meaning of it. What it says is Habuyoshi Fuharu, this is the grandmaster of shogi, the Japanese chess. He was beaten, and he says, from now, human beings are tested if we can understand a move driven by a computer algorithm, and we can drive the same move. That's what he said. So when it comes to the complex phenomena, this fourth paradigm may be effective. So I'm not sure if this is science, but this supports science. This can support science. And for this to happen, collaboration with experts or collaboration with data science, it's maybe necessary. And one additional page is something I would like to show you. The image about data is not fully shared amongst us. So relatively speaking, this is image to the image of, I think the image may be different from field to field. And sorry, I've already gone overboard with respect to time schedule, but I think there are two approaches. And just like database, the orientation of abstraction, or just like the information retrieval without abstraction, if you can do retrieval, then that would be sufficient. I'm struggling because I'm using this approach. So this is a promotion, but we got Kakenhi, the grants in aid for scientific research, and we are working on this approach. So we would be hopeful. We would like to make a presentation on these results. Thank you. Thank you.